yeah, just let me introduce you a little bit to our audience. So we have our remote speaker Attila Alkan. So he's a PhD student in Paris Saclay, and he will present today his progress on. So he's doing his PhD on natural language processing with focus on astrophysical data processing, and he's working for Astro-COLIBRI project. So it's a very nice platform for uh,
Aggregation.
Yeah, for aggregation of different sources of astrophysical, astroparticle events and so on. And yeah, I guess you're just gonna present Astro-COLIBRI and so your contribution from the machine learning side. Yeah.
Yes, exactly.
Yes.
Thank you, Dima, for your introduction. So I have split this presentation into three parts. First, I will explain you the context of my study, so which are mainly the observations time domain astronomy. In the second part, I will present you the main functionalities of AstroCOLIBRI, which is a platform that analyzes in real-time machine-readable format messages. And on the third part, I will present you the core of my research subject, which is developing natural language processing methods to extract information from these unstructured human written text. So let's start by the context of the study. So time domain astronomy, as you know, consists of observing tidal disruption events, fast radio bursts, gamma ray bursts, explosions of supernova, and so on. And these are observed by a large network of observatories around the world and space telescopes. And when observers detect an event, they will send alerts into the community. And these alerts are mainly in two kinds of formats. We have the human written reports, so the GCN Circulars, Atels, telegrams, and we also have these VOEvents, which are different forms. They are machine-readable format message. So yeah. So to deal with this machine-readable format message, we developed in our institute a platform that is called Astro-COLIBRI, and Astro-COLIBRI will allow us to analyze these VOEvent machine-readable format messages. So if you go to astro-colibri.com, you will find this web interface. This is the web interface of Astro-COLIBRI. And I will present you its main functionalities. First, we can see on the left panel of the window the map. So this is the events map. So we can visualize the latest detected transient events. All points on the map is transient events. So we can filter. So according to our preferences, we can filter these events. So for example, if we only want to get the transient event detected by a specific observatories, we can select. So on the map, the colors corresponds to the observatories which is implied in the observation. It can be the Swift Telescope, Fermi, Hawke, IceCube, and so on. And the icon corresponds to event type. For example, the stars, so the yellow stars corresponds to supernovas, the circles correspond to gamma ray burst, and so on. And we can filter by the type of events we are interested. Then we can also make a time window selection. For example, if we want to update this map and get only the information, so the information about the event that have been detected in a given time window, for example, the last week or the last month, we can here click on the buttons and select the time range. So as I said, possibility to display the events detected in a defined time interval. On the right panel, this time we can get for each transient events that we select on the map, we can get a lot of information. For example, AstroCOLIBRI is pointing to the VOEvents. By clicking here on the link, we have a lot of information about this event, its name, the detection time, and its coordinates, right ascension, declinations, the error in the uncertainty on its coordinates, the observatory which is implied, and so on. And here you can see we have a small piece of text. So we put this small piece of text mainly for hobby astronomers, because AstroCOLIBRI is not only a platform for professional astrophysicists, but also for hobby astronomers. And since hobby astronomers don't necessarily know what are supernova, what are gamma ray bursts, we put a small piece of text explaining them. But here you can see on the right side, we have a scientific mode button. And when we click on the scientific button, we can we go inside the scientific mode, and we can get, instead of this piece of text, we can get more detailed information. First, we'll see we again have the informations, a summary of the informations, but we have this visibility plots tool that allows for the astronomers, for the astrophysicists on different sites, on different observatories. It can be HEST, can be ATCA, ASCAP, and so on different observatories. We can know if a source, a selected source on the map is observable during the next 24 hours. So if we look at this plot, how to read it, so we can see that it is the visibility of a given source. We have its coordinates here, the visibility at HEST. So on the x-axis, we have the time. So it's 24 hours centered at midnight. So the first 12 hours corresponds to today, and the next 12 hours corresponds to tomorrow. The different color shape of grays corresponds to the beginning of the twilights. The black block corresponds to the dark night, and the gray, the brown window corresponds to the moonlight. And here we have the altitude limits, and we can see that this source is observable, for example, tonight from 1754 to 1850. So we have a small visibility window, and according to that, we can plan and trigger an observation during the night. Another functionality about that is that, so in AstroCOLIBRI, you can see, if you go in the platform, we'll see that we have more than 10 implemented observatories, but we can also compute that plot according to our own location on the Earth. Again, this is more functionality for hobby astronomers. Always they have small telescopes on their bag or on their garden, and if they want to trigger and to see if they can see an optical event, maybe they can trigger an optical event from their home. That's also why we give the possibility to compute the plot according to our own location. Another main functionality of AstroCOLIBRI is the consort. So when, for an event that we have selected on the map, we can zoom on the event and we can see if around the detected transient event we have other already known sources. So these sources are catalog sources on TEFCAT or 4FGL. So for example, these around our square icons correspond to 4FGL catalog source. So we can see that near the transient event, we have other sources. So maybe one question we can have about this, the detected emission from this source, is it coming from another already known sources or not? And so if we can answer to these questions with further more analysis. Yeah, and to do the consort, so we can put, if we know the name of the source, we can put its name, and we can also put its coordinates. We can query our database, see if it is in our database, and then we can trigger this consort. The platform is available. So as what I've shown you, it's the web interface. We also have the platform. The platform is also available on smartphone, so Android or iOS, whatever. You can subscribe, it's free, and you can receive in real time alerts. So if you use AstroCOLIBRI on your phone, you can go to the notifications menu and select if you want to be notified when a GRB is detected, or neutrino or other optical transients and stuff like that. So, and in real time, when you will receive a notifications about the detection of an event, you can see it on your map, check the visibility windows and stuff like that. So to conclude this first part about AstroCOLIBRI, so here you have the link of AstroCOLIBRI. We also give the link to our API, which has a documentation, so you can use AstroCOLIBRI, know how it works. And here the links to our two papers. The first, it's the paper to AstroCOLIBRI, and we published recently a second paper of AstroCOLIBRI. And as I said, don't hesitate to use AstroCOLIBRI, to download it on your phone. It's free, and either on the web interface or on your phone, you have the main functionalities. As I said, the main advantages with the phone version is that you have this real-time alerts pipeline. And don't hesitate to use AstroCOLIBRI and to contact us and give you your feedbacks. It's really important for us to continue improving the tool. Okay, and now we can move on the third part, which consists of analyzing these human written reports. So we have seen with AstroCOLIBRI that AstroCOLIBRI is able to analyze in real time these VOEvents, but on the other side, we have these human written reports. And for that, we don't have techniques at the moment to analyze them. So, and this is the core of my research topic. So if we look, if we zoom on these observation reports, so here on the left, you have a circular, and on the right, a telegram. These two documents, these two reports are dealing about the same astrophysical object. So this is the magnetar SGR G17452900. And actually, what we would like to do with this report is to extract all the information that are disseminated in different documents. But extracting information from astrophysics text, it's not an easy task. First, I can show you in blue, for example, here on the first paragraph, we use the designation of the astrophysical object. But on other paragraph of the same document, we make a reference to this event, so SGRG 1745, but using other terms, other expressions, the SGR, the burst, the event. And on the document on the right, we have the same phenomena, but we use other kind of expression, this intriguing source, the magnetar, the galactic center magnetar. And here, it is difficult for a machine to understand that all of these mentions on the text are related to the same object. And this is what we call coreference resolution in natural language processing. So natural language is the fact of detecting all the expressions, all the terms in a text that are referring to the same object. And this is a crucial step for information extraction, because imagine that on the right telegrams, you don't have the name of the event, and we only say this intriguing source, the magnetar, and we give a lot of informations. So it's energy, it's photon flux. We give a lot of information about this event. We would like to be able to detect these informations. So this is coreference resolution is an important task, and it's not easy for a machine to learn this. What I illustrate in pink is that it's really important to be able, when we construct a natural language processing model system, it's important to be able to detect all the informations that are dealing about the same event and which are spread in different documents, because some informations that I illustrate in pink are redundant from one document to another, but some of them are complementary. So it is also able to extract. It's also important to be able to extract this complementary information. Yeah, and another aspect due to the language, and which is also difficult, very challenging, is the phenomena that we called uncertainty in the expressions and also negation. So, for example, if we read the last paragraph, they say that it is possible that actually the magnetar, the emission that has been detected, it's not from the magnetar SGR 1745, but it may be emitted by another source. And so the natural language processing system that we will build, it's really mandatory that the system has the capacity to follow very thin information on the text that may invalidate first informations. So this is very important. So first, so basically what we want to do, so we want to extract all the information about a source and to build a knowledge base for the astrophysics domain. So get the name of the event, its type, its wavelength, its flux, and so on. So to do this information extraction task, one possibility approach is to do named entity recognition. But what is named entity recognition? So also called NER, it consists of recognizing mentions or concept in a text that belongs to a predefined semantic type, so name of person, of location, of organizations, and also all the properties here in our case, all the properties about a given source, its coordinates, and its frequencies, its wavelengths. For example, here you have an illustration of a named entity recognition task. You can see that here the model is able to recognize the name of the observatory. So Chandra X-ray Observatory, the name of the detected source, how many times they observe the source, the date, its coordinates, and also to be able to extract references to other circulars or telegrams that are dealing about this object. So this is named entity recognition, and this is the approach I propose to extract information. How we do that? So first, we need to collect data and to build a corpus. And this is what I've done during the first year of my PhD. I built the TDAC corpus, which is the acronym of Time Domain Astrophysics Corpus. To do that, I have extracted all the circulars, telegrams, and AstroNotes from the transient name server from 1997 to 2021. So my corpus is composed of more than 45,000 documents, and to build my named entity recognition system, I'm obliged to annotate manually some of these documents. So I have annotated 75 documents. So yeah, 75 documents that are annotated to build named entity recognition system. The problem, 75 documents, it's a very small corpus, and the question is that how to tackle the lack of annotated data for named entity recognition, because language models based on neural networks requires a lot of annotated data, and here we only have 75 documents. So the questions that I've asked and I wanted to explore is to see if is it possible to learn from an other astrophysics corpus, which is bigger in size, to proceed to an automatic pre-annotation of the TDAC corpus. So basically, is it possible to learn from other astrophysics text and to transfer this knowledge on the observation reports to extract information from these observation reports? And the second approach that I'm exploring at the moment is to investigate the data augmentation methods, so to create artificial data to train language models. So the first experiment I did was based on the DEAL corpus. The DEAL corpus, it comes from a researcher from the University of Harvard, from the Center of Astrophysics. they built the deal corpus, which is composed of astrophysics papers. So these are different from observation reports. And I wanted to see if a system built and trained on astrophysics papers would be able to recognize the same concept and the same information requires on using the observation reports. And we can see, if we look at the F1 score, we can see that the performance decrease a lot when we want to apply it on observation reports. So we have a decrease on the F1 score. So probably this poor performances on observation reports, it's mainly due to the fact that both corpora have distinct corpus properties. So on the one side we have astrophysics papers, and the other side observation reports. The language is a bit different, the topics are different, and the structures of the documents are different. That's probably why we have poor performances. And at this stage, I wonder if is it better to continue the fine-tuning of the system that we built using astrophysics papers and to continue its fine-tuning on observation reports, or is it better to build a system from scratch on observation reports? And here, these are the results. We can see that so the experiment 2 is when we continue the first fine-tuning we done on astrophysics papers, and we fine-tune it on 9 additional epochs. And on the experiment number 3, I fine-tune a model from scratch. And when we see at the final results, we can see that fine-tuning a system from scratch, it's not so useful. It's really useful for the Atels, but overall, when we look globally, we can see that actually fine-tuning using astrophysics paper as a starting point to continue and then continue to learn on astrophysics observation reports looks like it's a better option. And then, as I was mentioning, is that at the moment I am investigating data augmentation methods. So for that, I mainly propose 3 methods. The first method consists of, let's say you have a piece of sentence, documents, and what I will do, I will substitute some tokens, some words of this corpus by other. For example, espadons, which is the name of an instrument, I will replace by another name of instrument, and then I will create my my artificial data. Other kind of approach, so the method number 2 and 3, consists of using language models. So when you use a language model, you can mask a word and you can ask to the model to predict the masked words. And that's what I did using different language models. So I used Astrobert, Cybert, and Roberta. These are language models, and I masked some instrument names, observatories name, object names, and stuff like that, and asked the models to predict the masked words. The problem when we are using a language model is that it's possible that the name of the instrument we masked, the model will predict another word which is not a name of an instrument. And this is a really important problem when we want to train a system able to detect name of instrument, of observatories and stuff like that. So what I test on the third approach is to train a system, a language model, which will try to predict the masked words, but adding before and after around the masked word the category of this word. So if I mask a name of an instrument, I will add around this specific tokens to say, okay, the words you need to predict is an instrument. And when we fine tune the system like this, he will be able to create a new artificial data which is correct, so we don't have an error between the words, the predicted words, and its category. And I've conducted on the first experiments I have conducted, we can see that the performances are model dependent. So as I've said, I use AstroBERT, which is a model trained on astrophysics text only, Cybert, which has been tested on general scientific text, and Roberta on general language corpus. And we constate that we notice that it's not AstroBERT that performs the best. Roberta, which is a model that has been trained on general English, performs well. And we also noticed a threshold effect depending on the size of the corpus. And this threshold effect is probably due to the fact that the artificial data we generate is very close to the original data, because you have seen that we mask a token and we predict another tokens. So we substitute. And the structure of the documents remains the same. So artificial data and original data are very close, and probably that there is an overfitting. And at the moment, I am exploring. I'm continuing my experiments, and I am producing new annotation to increase the size of my data. And I'm also exploring different approach for this data augmentation. The objective would be to change the context around the mask tokens to add diversity to the artificial data we create. And also, I will also start to work on coreference resolution. As I was explaining on the beginning, coreference resolution is the fact of detecting all expressions mentioned on the text that are referring to the same object. And we hope for the end of the PhD that once the models we build, the language models we build, will be considered enough reliable. These language models, we hope that it will enrich the Astro-COLIBRI platforms, and then Astro-COLIBRI will be also able to not only evaluate and analyze machine-readable message, but also these human-written messages. So thanks a lot for your attention. I hope it was clear and it was interesting.
Yeah, thank you very much. Let's thank the speaker.
Thank you.
Thank you.
Yeah. So actually, regarding Astro-COLIBRI, I just make a side remark that here, when I came here, there is actually like astronomers community. Yeah. So send to our chat, and maybe we're gonna advertise Astro-COLIBRI because I like amateurs.
Mm-hmm.
So maybe you will acquire new users. Yeah, so I don't know whether we'll have a chance to meet with them in person or to participate in some observations, but yeah, we'll definitely advertise Astro-COLIBRI.
Yes,
Yeah,
thanks a lot, Dima. Yeah, thanks a lot. And really, we can continue to improve when we have your feedback. So the more we have feedbacks and user, the more we can improve Astro-COLIBRI.
yeah, I see there's a visible progress since the last time I have checked it out.
Yes, thank you.
I have one little question regarding the deal data set.
Yes.
Have you tried to check whether it is overlapping with any huge popular data sets like Pile or etc.? I mean, what if like BERT or other like foundational language models already contain the data from deal in their training data set? Have you tried to check for duplicates, whether the deal is contained in well, somewhere else?
Yeah, exactly. There is the risk that the deal corpus already contains data from other corpora, and the inverse can be also true. But actually, when I look at on the literature review, there are very few annotated documents in astrophysics. There are very small corpora, very few, and these are not actually accessible. The only corpora which are accessible is the DEAL dataset and the TDAC corpus. And between both corpora, there is no an overlapping because they are based on really different type of documents. DIL is piece of astrophysics papers, and TDAC is really based on observation reports. But I totally agree the fact that we could have some risk of overlapping between probably maybe the other astrophysics corpora that are not available.
Okay, I see. Thank you.
You're welcome.
Okay. Other questions from audience? No? Okay, then I ask one more. Could you please go to slide number 16, I believe?
Yes.
Yeah, I mean, yeah, just maybe 15 without this central table.
Yeah.
Yeah, so it's actually a very nice observation. I mean, on the right panel, I just indeed like thinking about this, that those you highlight with the light with a blue color, especially like the intriguing source and blah blah blah. So I guess it's like I kind of never noticed this when reading the paper as a human, but actually this kind of emotional coloring, maybe we should deny this in science, yeah, right? Because it's like indeed it increasing the size of the texts, and this maybe not needed. What do you think about this?
Yep. Can you please just repeat your question, please?
Yeah. So my question. So what do you think? Whether we scientists should kind of deny this emotional coloring of our papers, because I mean, first of all, it's just increasing the length of the text, yeah, at all, as a word count, and the second, so it's can give some some additional problems for automatic processing, right?
Yeah, exactly. And actually, this phenomena occurs not on astrophysics text, but also on other kind of text, or on biomedical domain, on clinical domains. It appears in all phenomena because, and it's difficult really to deal with that and to maybe avoid that, because it's language, it's the way we share informations. So that's really maybe difficult to deal about. And actually, I would say something before forgetting. You can see on the blue phenomena that are highlighted that the name of the events between both documents are not the same. So G1745 and here it's 25, but both documents are dealing about the same object, and this can also be can be really problematic for natural language processing. It's the errors given included by the human when they share informations. And I've checked, actually these objects are the same, but the official name it's G1745 and G1725. It's not I don't know if it's a different source or it is a non-existing sources, but this is a mistake. And if we are able to build a coreference resolution system, maybe we can nevertheless extract all the information, even if there is an error on the designation of the object.
Yeah, that's really interesting. Actually, I think that we could try to use like this NLP approach to try to detect the emotional color in papers or other messages.
Exactly, yeah. Exactly.
But why do we need to detect emotional color? Just for fun, or?
No, just to report like your paper doesn't sound really scientific.
Yeah, it's similar what Grammarly is doing.
Yeah, or we could just red flag some parts of text.
Yeah.
Well, I mean for other neural networks. When you're extracting information, don't extract these particular words, for example. Don't.
Yeah. Okay. Yeah. And do you consider that the last paragraph it's also emotional? For example, when they say that it is possible that, for example, because it's not a certainty, is the author, when he writes the document, it's not certain about what he said, and maybe it's also important to be able to extract the fact that, okay, about the information we extracted, maybe it's not reliable 100%, and we should pay attention, or it will requires more a manual human analysis.
I guess when one uses like word possible, it's relates to probability, so it's fine. It can be kind of quantified. Yeah, right.
Yeah.
Yeah, but I mean, the intriguing source, I don't know. I mean, honestly speaking, sometimes maybe this included only because of the word count limitation. Yeah, people just try to add a bit more, I would say, useless language construction in scientific text, because you remember, I guess, what is the time? So are we fine with time? I don't know when the next one is scheduled. Okay, we have next speaker, but anyway, so we have workshop. It's fine. Yeah. Yeah, you remember that the scientific texts were kind of inflated. I mean, when you read like yeah, papers written like 50 years ago, yeah, so they were rather short, like 2 or 3 pages, yeah, but and actually contain much more content.
Yeah.
Even we do not have, let's say, an electronic tools for yeah, for text formatting and the for formulas. But now, I mean, we have like incredibly long text, like 15 pages or so, or 10. I mean, I guess the average size of the paper, like 10, 15 pages, like inflation in factor of 3 or even factor of 5.
Okay.
And this, yeah, also an issue because, I mean, I wouldn't say that science became more sophisticated or more smart than 50 years ago. Yeah, so the texts just were simply inflated.
Yeah.
And I also see this as a problem, and maybe, yeah, we
Exactly.
can
Yeah.
use a machine learning to compress it back.
Yeah. Exactly. We
Because,
can. Yeah. Yeah.
Or at least indicate that it could be compressed.
yeah. or yeah, and it's not a machine learning problem, but it's like, yeah, it's like kind of
Yeah. I see.
social. And when it's
One moment.
1 more minute, so for before next. Okay. So if there are no further questions, thanks Attila again. So if you have time, please stay for next talk, because it will be like on the same domain as yours, and so we can discuss
Okay.
together.
Perfect.
Okay. So
I can stop sharing my screen.
yes.